So without further ado, I think you're probably going to need an introduction to most of the audience here. And we will talk about the spectroscopy of the fake positonium molecules.
Got two of them as well. Hello, so I'm going to be talking about slow decay processes in electrostatically trapped Rydberg states of both nitrogen molecules and nitric oxide molecules. So the motivation behind this, so we wish to study slow decay processes of long-lived Rydberg states of atmospheric molecules. And by slow decay processes, I mean states or decay processes that happen on hundreds of microseconds timescales for molecules that live on that sort of timescale. So the reason we also want to do this is because we wish to prepare cold samples of neutral molecules that could otherwise be laser cooled or decelerated or trapped in their ground states. So previously in ETH Zurich, some people did, well, Frederick and Stephen did, and H2 and D2. And in the UCL, we've done some trapping of NO and N2 molecules. And such deceleration and trapping can also be used to perform ion molecule reactions, as you might have heard from the Martin poster. So first of all, we'll start with nitric oxide molecules. So to get to the high Rydberg states, we have to use a resonance-enhanced two-color, two-photon excitation scheme. So we go from this ground doublet high half state to the intermediate A doublet sigma plus state. And then from there, we can excite into these high Rydberg states of either P character or F character. However, the F character states are more conducive to mixing into the long-lived start states because of a much smaller quantum defect. And this is done because of the presence of ions and electrons at the time of photoexcitation. So once we've excited these states, how do we trap them? So we do this using the fact that in the presence of an inhomogeneous electric field, the molecules undergo a Stark effect. So therefore, well, in a electric field, they undergo a Stark effect. So if we place these molecules in a region of inhomogeneous electric field, and they go from a region of smaller to larger electric fields, the potential energy is increasing whilst the kinetic energy is decreasing, which results in a force acting on the molecule in these low field seeking states that acts towards electric field minimum. And this force can therefore be used to control the motion of molecules in these high Rydberg states. So what kind of states are we going to be decelerating this experiment? And so Harold is hoping for a figure that looks something like this. But for different n plus. So if we assume that we're in Mn is 0, we have this very complicated Stark map where we have all the low L character states present. This is not very conducive for deceleration because these low L states have fast non-radiative decay times on the order of hundreds of nanoseconds at best. So their presence and mixing into the Stark states leads to lifetimes that are on the order of 1 microsecond or so. However, if we go to higher MNs, these low L states have been removed from the Stark manifold, and therefore the lifetimes you get at these stellar states would approach fluorescence decay times because we've removed these fast non-radiative decaying states. So these are the states we are preparing this experiment and that we are decelerating and trapping. Okay, so back to the decelerator. So we use a chip-based Rydberg start decelerator. So we have a supersonic beam venom that enters into this chip region, which consists of an array of square electrodes of 0.5 millimeter size, 2 side electrodes, and this upper plate electrode. To generate the electric field traps, we apply a series of 5 repeating potentials to this array of electrodes, and then a constant potential to this upper plate electrode. And this generates electric field distributions that look like this. So this is a slice through the center of this decelerator. However, the molecules are traveling too fast and too much kinetic energy just to raise these traps straight away and trap them. So we have to oscillate these applied potentials with time so that this electric field minimum moves along this array of electrodes and therefore transports the molecules in these high Rydberg states as it moves along around this electric field minimum. If we then were to oscillate these applied potentials with time, such that the electric field minimum slows down as it travels along this array of electrodes, we can therefore decelerate the molecules with this trap and ultimately bring them both to rest in the experiment to then perform decay measurements. So again, here is a schematic of the experiment. So here's the supersonic beam venom comes in here, is intersected by 2 counterpropagating pulse lasers. the Rydberg state of NO are then loaded into these moving electric field traps here, transported to a detection position where pulse electric field ionization is used to detect the molecular ions of an MCP detector. This all happens inside the 30 Kelvin heat shield as well, I should say. So first of all, we can perform the experiments with no guiding potentials applied, and the electrodes are grounded, and we can just measure the time of flight from this excitation to detection position. We find we obtain this black time of flight curve. We see this is kind of wide, and this is because there's a distribution of longitudinal beam, and so therefore they disperse as they travel this 100mm distance from excitation to detection. However, if we turn on the guiding potentials and oscillate at a constant frequency, we'll guide the molecule, the traps will move at a constant velocity and guide the molecules with it. We therefore attain this red time of flight distribution, which we see is much narrower, which indicates the molecules have been loaded into these traveling electric field traps and effectively transported to the detection position. If we then decelerate these traps with time, we can find that the time of flight distribution is shifted to later and later times, showing that the molecules have been effectively decelerated in these moving electric field traps. It doesn't take much more deceleration to ultimately trap these molecules above this detection position and monitor how the population changes with time. So here's an example of such a decay. So here T0 is the time the trap is brought to rest. We see we measure trap decays on the order of 1 millisecond. And we can fit a single exponential function to the early trap decay time to extract ITAMP. The reason we have this non-single exponential decay is attributed to the fact that we're actually populating a distribution of start states in the experiment. And these states have a distribution of lifetime, some of which are going to be longer lived and some of which are going to be shorter lived. So therefore, as time goes on, the relative amount of longer lived states will increase. Therefore, we get these longer trapped, longer lived states at these later times. And so therefore, to extract information about the trap decays, we fit a single exponential to this early time because it is more representative of what was initially populated and trapped. So then the next question is, well, for what range of Rydberg states can we perform this deceleration and trapping? And so to assess this, we formed a Rydberg excitation spectra where the detection occurred after the deceleration and trapping process, so after trapping for 350 microseconds. And we see that we can consistently excite molecules on these NF M+2 resonances. Although we can excite molecules in these other resonances, I'm just going to focus on these NF M+2 resonances in this talk. And the reason we have this sort of shape to the spectral intensity in the trap is because at lower values of the principal quantum number, the efficiency of the trapping is limited by the dipole, which goes with the n squared, and at a higher value of the principal quantum number, the efficiency of trapping is limited by the n to the minus 4 dependent, of the electric field ionization, which effectively limits the phase space volume of the trap that can be used during the deceleration process. So now we know which range of molecules we can perform these experiments for. We can trap them on molecules in these states and measure how they decay from the trap. And we find that we measure trap decay times that are on the order of 400 to 200 microseconds for NO. And the fact that these measured trap decay times in fact decrease with increasing principal quantum number, which is not as you'd expect from an atomic system where you typically expect these to go with n to the 4. In fact, you can make a comparison to the calculated fluorescence elements start state lifetimes, where you see that this trap decay time, the decay time due to fluorescence should be increasing with increased principal quantum number, as we'd expect. So, why do we see this general trend going down? Well, the reason for this is because actually there are some nearby low end states in the first vibration excited series that lie close by to the highly excited Rydberg star states we're exciting this experiment. However, these states have lifetimes that are on the order of 1 picosecond. So therefore, if we have a 1 pass intensity line mixing of this character into these states, it would contribute 1 kilohertz approximately to the total decay rate of these states, which, given that you'd expect the fluorescent decay rates of these states to be also on the order of 1 kilohertz, means that this contribution from this mixing into here, even at a very weak level, would become significant. And this mixing occurs because of the effects of charge multiple interactions, which can couple Rydberg states that exist in 2 different rotational vibrational series. However, we also have deviation from this general trend that we see in the data, And we think these are to do with charged multiple interactions within the Rydberg series. So as excitation, here we see some states that we measured trapped decay times below the general trend. And we attribute this to the fact that we think we're populating a statistical mixture at excitation of 34 M+2 dark states and 32 M+3 dark states, and also these ones in this case, because of near degeneracies between an optically accessible state and a state that is mixed in because of charged dipole effects. We also see this in the state that I've seen above the trend with charged quadrupole effects, where we were mixing the M+2 states into M+0 states as well. So the fact that these states have lifetimes that, trapped decay times that deviate from the general trend suggests that the states that are being also populated in these instances have different decay times, though, so the decay time must depend on the M+ rotational state of the Rydberg states. And so we did some further measurements of this, where we measured the rotational dependence of this trapped decay for states where M is 40, for M+2, 4, and 6. And we do indeed measure that as we increase the rotational quantum number, that the measured trapped decay time decreases, but in this case by an order of magnitude. So therefore, these rotational states in NO have been observed to have different decay times that depend on their rotational quantum number. We also did some experiments where we excited to the first vibration excited state of NO and performed very similar measurements, and we see a very similar trend in the data. And then we can infer from this that the effects of vibrational autoionization on these states that are exciting in the experiment must be minimal, so we can constrain it to less than 60 Hertz. So in NO, we have a case where the leading order terms of these charged multiple interactions will be charged dipole interactions. So it's actually useful to go to a case where we have a homonuclear molecule where such effects can't be seen because there is no charged dipole processes with the leading order terms being charged quadrupole. So to do this, we decided to attempt to do experiments with Rydberg states of N2 molecules, and ultimately this led us to the first trapping of N2 molecules. So the excitation scheme we use is from the ground state in the sigma Gerard plus state to the atypical prime sigma Gerard plus state. And then from there, we can excite to very similar NP or NF Rydberg states that are associated with the ground electronic state of this iron core. And again, we expect these NF states to be the ones that consistently mix into these long-lived Rydberg start states that we can decelerate and trap in the experiment. So first of all, we just did a spectra of the long-lived Rydberg states in the supersonic beam with the detection happening at the late detection place 100 millimeters after photoexcitation. And we can see that compared to the NO, we have a much more complicated spectra, but that we can still consistently see excitations on these NF Rydberg state resonances, and that the fact that this detection happened 130 microseconds after photoexcitation means that these states must be these long-lived Rydberg start states that we populated in the NO experiment as well. Then similarly, we performed a spectra in the trap where at 350 microseconds after photoexcitation, and we can see again that these NF resonances are dominating the spectra with some other features, which I'm not going to talk about now. And so just to show that we are actually trapping this, here is first of all the same measurement as I showed for the NO, but just demonstrating the decelerator off setup where we just let the molecules fly through and measure the time flight. And then we can see here the guiding of the Rydberg N2 molecules and then deceleration to various velocities. We then measured their trapped decay time. So the top panel shows it on a 1 millisecond timescale. And we can see that the decay is much longer than in the case of NO, with a decay time of around 600 microseconds. And indeed, this meant we could actually perform trapping experiments on the timescales of 10 milliseconds. So you can see here this in the bottom panel, and you can see as time goes on, we have this non-exponential decay, which we attribute to the distribution of states in our experiment. So we can then compare what we measured for the case of N2 to what we measured for the case of NO. We find that as we increase the principal quantum number in N2, that actually our measured trapped decay times increase. which is reassuring. And then compared to this NO case where we saw these trap decay times decrease with increasing principal quantum number. So lead us to infer that the most likely reason for this decrease is in the NO cases to do with charged dipole interactions, which are just not present in the case of N2. And even further, we've recently done some experiments with some Rydberg states of helium in its singlet state to measure the trap decay time. So in this case, it's not a high M state, it's M, we think is NL is 0 and 1, probably most likely in the distribution of these 0, 1, maybe 2. We need to work them out. States. Now again, we see that this trap decay time generally is increasing with increasing principal quantum number, which is even more suggestive that this is definitely some discharged dipole molecular effects. And also we see that this is changing continuously and doesn't have any weird, doesn't have any drops that are associated with these rotational charged multiple interactions as well. Right. So with that, I would like to bring my talk to a conclusion. So we've demonstrated the ability to deceleratively track long-lived Rydberg states of NO and N2 on these timescales of up to 10 milliseconds. We've used this to demonstrate the ability to prepare cold trap samples of molecules in excited high-end Rydberg states and use this to perform prepare velocity controlled beams. And we've then used this to perform investigations of the effects of rotational vibration excitation on the trap decay times, as well as infer the effects of charge multiple interactions on these decays. With that, I'd like to thank you for your attention.
One question.
Yeah, I'm just curious why you needed the cold trap. Is there a lot of black body radiation that would ruin the experiment? I'm curious why.
Yeah, so if we perform these at room temperature, the trap decay times are significantly shorter because the effects of black body transitions and ionization. So performing at 30 Kelvin just shields it as much of this black body us from as much of this black body radiation as possible, basically.
You have a quick question? I just want to make the case. So, that's the big honest, but yeah. Why is there no personal non-decelerated to design for the ones that are not being matched?
So you're saying why would you not see the unguided ones in there? Because they're all just sort of they're mostly all being loaded into the trap. And so any ones that are not loaded are probably being ionized in the high fields at the edges of the trap. And so therefore you're not getting a signal from these not decelerated ones. And they're not just because they're not dispersing, they're not going to make it like a long tail out to either side either.
Thank you, Matt.